All right, let's go ahead and talk about the strength of acids and bases. And so we're going to talk about strong acids and weak acids, and strong bases and weak bases. And so acid strength is measured by the size of the equilibrium constant, which is K. And that's when it reacts with water. And so what we want to think about is acids are anything that donates a proton. They donate a hydrogen ion to solution. So as they go into solution, they're going to give off a hydrogen ion. And so that's what we want to think about when we talk about acids. So we want to remember that. And the strength of an acid really is dependent on how much the hydrogen is attracted to the conjugate base. But the equilibrium constant for this reaction is called the acid ionization constant, which is the Ka value. And the reason why it's A is because they're acids. And then there's things called Kb values, which are for bases and all that. So the Ka value tells us how strong an acid is. And so the larger the K value, the larger the Ka value, the stronger the acid. Because if you think about it, what is the K value? It's product over reactant. And so if you have something that is going to give off a lot of hydrogen, where it's going to favor giving off hydrogens, it's going to be a strong acid. Now, on the other hand, a weak acid is something that does not want to necessarily give off its hydrogen. It's going to want to hold on to its hydrogen more. It will give it off occasionally. It will give off the hydrogen, but the amount of hydrogen that's given off is smaller, and so it's a weaker acid. And so, again, the larger the K value, that means the more product is produced. That means the more hydrogen ion is added to solution. And so I'm going to go back a slide here, and we're going to take a look at that bottom equation. And that's kind of what we want to think about. So we have HA yielding H plus A. The larger the K value, the more H and A are separated. The smaller the K value, the more H and A are together. So the more reactants there is. So a strong acid or base will ionize 100%. So that means if we put 100 molecules of a strong acid in solution, 100 of them will dissociate. So that means we will have all H and A, so it'll all be product. And so none of the hydrogen ion and conjugate base will stick together. All of it will 100% dissociate. And so if you take a look, this is a great example. When the HCl goes into solution, notice how there's no hydrogen and chlorines that are still together. So we end up with hydrogen ion in solution, and we end up with chloride ion in solution. There's no hydrochloric acid that is still in solution that's together. The hydrogen and chlorine are not together. Notice how we indicate this with a single arrow, because it 100% goes to product and it doesn't go backwards. Now, the equilibrium lies far, far to the right. That means that it's pretty much all product. And so that means you're going to have a very, very large K value, because again, it's product over reactant. So if you have mostly product, it's going to be a very large K value. And so these tend to be strong electrolytes, because they 100% ionize, they're strong electrolytes. Now, since a strong acid and base dissociates into ions, the concentration of the hydrogen ion concentration in solution is going to be equal to the original concentration of the acid or base respectively. So that means, like, if we have a 1 molar solution of HCl, because HCl is a strong acid and it 100% dissociates, that means we're going to have a 1 molar solution of hydrogen ion also, because all of the HCl is giving off the hydrogen ion. Now, something to note is if you have something like calcium hydroxide, notice how for every 1 calcium hydroxide, there's 2 hydroxide. So notice how, because there's twice as many hydroxide, that means if you have a 0.1 molar solution of calcium hydroxide, you're going to have twice as much hydroxide, because again, every one of those gives off 2. Also, don't confuse molarity, which is concentration, with strength. So don't confuse molarity with concentration. You can have a large molarity of a weak acid, you can have a small molarity of a strong acid, and so molarity does not mean strength. All right, so here's a list of some strong acids. These are ones that you should memorize. It's pretty straightforward. We have the chlorine, bromine, iodine. So right there, if hydrogen's with one of those three, strong acid, and then we have nitrate, sulfate, and chlorate, perchlorate. And so those are the other three strong acids. The other thing too is if hydroxide is with anything in the first or second column, strong base, 100% dissociation. All right. Now, when we look at the polyatomic ions, we have something like hypobromite, bromite, and bromate. So when we look at those, notice how each one adds an oxygen. When we look at that series, like bromate, bromite, hypobromite, the more oxygens there are, the stronger that acid's going to be. So the one on the very right is going to be the strongest. The one on the very left is going to be the weakest. All right, so let's talk about weak acids. A weak acid or base does not completely ionize. So what that means is if we put 100 molecules of a weak acid in solution, not all 100 of them are going to be dissociated. And so notice how HF, when it goes into solution, notice how some of the hydrogen and fluorine are still together. And we do end up with some fluoride ion in solution and some hydronium ion in solution, but the reality is most of it actually sticks together. The hydrogen and the fluorine really do tend to stick together. And so because of this, because not all of it is given off in solution, it's considered a weak acid. And so it says there that usually less than 10% is ionized. So in this situation, if we put 100 molecules in, only 10 molecules will actually dissociate at any given moment, because as they dissociate, they start to come back together. But the reality is that it's even way less than that. There's most weak acids can be a very, very small percentage are actually ionizing. It could be even less than it's a decimal, a percent of a percent even. So for weak acids, the equilibrium position is far to the left, which means that it's reactant favored. They have a very, very small K value, and they are considered weak electrolytes because they don't provide a lot of ions to solution. The vast majority of acids and bases are weak acids and bases. So think about that list before strong acids, there was only 6 of them. Typically, the hydrogen ion concentration is less than the concentration of the solution, the acid solution. So, for example, if we had a 1 molar solution of HF, because not all of the hydrogen ions is being given off, we're going to have less than a 1 molar solution of H. And we're going to look at an example problem of this in the guided practice. And that's it. So here's the main thing. Strong acids, 100% of the molecules will dissociate. If you have 100 molecules of strong acid, you'll have 100 molecules that are dissociated. Weak acids are the opposite. They don't 100% dissociate. In fact, they tend to stick together more than they let go, than they give off their hydrogen. The other thing too is the concentration of a strong acid will be equal to the concentration of its hydrogen ion if it has 1 hydrogen ion, and those are pretty much the main concepts. The other thing we want to keep in mind is that the K value, the larger the K value, the stronger the acid. So keep that in mind as we do these guided practice problems, and definitely come to class with questions, and have a good day.